Hi everyone. We will be looking at Briggs section 3.1 today. We are introducing the derivative. Okay? And a lot of this section is going to be connected to when we first introduced limits. Okay, so if you remember when we first introduced limits, okay, we looked at the average velocity of a function s of t on some interval from a to t. And we said that the average velocity was the slope of our secant line through our 2 points. And the slope was given by, or our average velocity is given by our slope formula. Okay. Now, this is the same as our average rate of change of our function on an interval. Okay, so our average rate of change we can formally define. So our average rate of change in f on some interval from a to x, okay, is the slope of the corresponding secant line, m sec, okay, where we're finding the slope between f of x, or a f of x, or sorry, x f of x, and a f of a. Okay, where we know what the point A is, we're given that. X can be any point on the line, or function. Okay. We can also, or back when we defined the limits, we defined the instantaneous velocity of a function as the limit of the average velocities as t approaches a, okay, where we used our v with the little I in st, and we gave it using this formula. And so our instantaneous velocity, okay, remember that was the slope of the tangent line at our point. Okay, so if you remember, we had some function, we had 2 points. We had our secant line. Okay, and the slope of this line is our average rate of change. And we had our tangent line. We have some function. I'm looking at a point here. We look at the tangent line. That's going to be our instantaneous velocity. Okay, or it's the same as our instantaneous rate of change. Okay, it's given by the limit of all of those, or all the possible secant lines. So if you remember, I drew a picture in class. It looked kind of like this. We had all the possible points it could be. And as our possible points, and we had our secant lines. And if we take the limit of these possible, or of all possible points, with the limit of the secant lines of all the possible points, we end up with the slope of our tangent line. Okay, so that's our instantaneous rate of change as well. Right? So it's the slope of that tangent line as long as that limit exists. Okay, and then the tangent line is a unique line through this point with our slope, that's our instantaneous rate of change. And the equation for our tangent line is given by y minus f of a equal to m tan, or the slope of this tangent line, times x minus a. Okay, and we can do an example. In an example, they would say something like, find the equation of the line tangent to the graph of f of x, which in this case is going to be equal to 3 over x, at the point 2, 3. Okay, so we were given this point 2, 3. We know that it is a f of a, or equal to a f of a. Okay, so 2 is a, 3/2 is f of a. Okay, and we'll use that in a minute. But first, before we can find the equation of the line, we need our slope. Okay, so we'll have to find m tan, which is equal to the limit as x approaches a, which in this case is 2, of f of x minus f of 2 divided by x minus 2. Alright, we can plug our actual function in here and we get the limit as x approaches 2 of 3 over x minus 3 over 2 divided by x minus 2. Alright, and so then in this next step what I'm going to do is take, we've got this fraction inside of another fraction. So I'm going to rewrite it so that way I've got my numerator times 1 over our lowest denominator. Okay, and then I'm going to find a common denominator and combine these numerator. Okay, so if I find a common denominator and combine these two fractions, I end up with 6 minus 3x divided by 2x. Okay, and then I can have that times 1 over x minus 2. Okay, and then we can multiply those fractions and we get the limit as x approaches 2 of negative 3 times x minus 2 over 2x times x minus 2. Okay, our x minus 2's cancel. And we end up with a limit as x approaches 2 of negative 3 over 2x, which is equal to negative 3/4. Okay, and this is our slope of our tangent line. So we can use this and find our equation for our tangent line. So we know our equation for our tangent line is going to be of this form. Okay. And so we can take and plug our pieces of information that we know in. So that in this case would be y minus f of 2 equal to negative 3/4 times x minus 2. We know that f of 2 is equal to 3/2. Okay, and then we can solve for our equation. Okay, and what we get is our equation of the line that is tangent to f of x equal to 3 over x. Okay. Now, you won't have to write all of this out, but you do need to recognize what this line is and what this equation represents. Okay, so it's the equation of the line that is tangent to our function at x equal to 2. Okay, because that was our a value. Okay, so there's using that average rate of change and instantaneous rate of change formula. Okay, there's another way we can look at average rate of change and instantaneous rate of change is if we look at some function and instead of looking at it on an interval from a to t, or sorry, a to x is what we used, where we knew a but we didn't know x. Okay, this time if we want to look at it on a function that's from a to a plus h. Okay, so now we're going to know a. Okay, we don't know h. So h is just the difference. If I have a function, some function, I know what my a is, I'm going to add h to it and get a plus h. Okay. And so we look at if we apply our slope formula to this to find our slope of our secant line, what we end up with is the a's cancel in the denominator. And so we end up with f of a plus h minus f of a divided by h. Okay, but still the same slope of the secant line. So that's our average rate of change, and then our instantaneous rate of change is just the limit as h approaches 0 of that average rate of change formula. Okay, so beforehand, if we look back, we had our average rate of change, okay, and our instantaneous rate of change was the limit as x approaches a of that average rate of change formula. Okay, down here we have the same thing, but instead of x approaching a, we're going to have h approaching 0, because h is what's in our denominator. Alright? And this is still the slope of our tangent line at whatever point a we're given. Okay, and again, this is contingent upon that limit existing. But we can use the same process to do some examples. Okay, so if we're looking for an equation of the line tangent to the graph of f of x given here and at our point 1, 5, where remember 1 is a, 5 is f of a. Alright? So we can follow the same sort of process. We're going to find our m tan first, that slope of the tangent line. And this time we're going to use our new instantaneous rate of change definition. We can use either one, but I want to show you how this one works. So in this case, we're looking for the limit as h approaches 0 of f a plus h. In this case, we know that our a is 1. Okay, so we have the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. Okay, and so we'll plug in our formula, or not our formula, sorry, the equation we were given for f. Okay, so I end up with 1 plus h cubed plus 4 times 1 plus h minus 1 cubed plus 4 times 1, all divided by h. So what I have here is my f of 1 plus h. I make sure I plug 1 plus h in anywhere there's an x. Okay. And then I have my original function with just a plugged into it, divided by my h. Okay, so I expand this out, making sure Remember, you cannot distribute that 3. Okay? This is really 1 plus h times 1 plus h times 1 plus h. Okay? Now, if we do that, we expand it all out. And we get the limit as h approaches 0 of 1 cubed plus 3 times 1 squared times h plus 3 times 1 times h squared plus h cubed. And all of this, and some more sum. Plus 4 times 1 minus 4h. Okay, now we got it all. All of this comes from this first piece. Okay, which is okay. It looks a little messy, but it's okay. It's what we're supposed to get. We've got to expand it out. Okay, and then we have minus 1 cubed minus 4 times 1, making sure we distribute this negative to both terms. Okay, and all of that divided by h. And so if I look at it, I say, well, I've got a 1 cubed here that's positive and a 1 cubed here that's negative. And a positive 4 times 1 and a negative 4 times 1 that will cancel for me. This leaves me with the limit as h approaches 0 of 3h plus 3h squared plus h cubed minus 4h divided by h. I've got an h in each of those terms in the numerator, so I will factor it out. H times 3 plus 3h plus h squared minus 4. All divided by h. I can then cancel my h's. And I'm left with the limit as h approaches 0 of 3 plus 3h plus h squared minus 4. Now, I've gotten rid of that pesky h in the denominator, and I can plug my 0 in now. So I end up with 3 plus 3 times 0 plus 0 squared minus 4, which in turn gives me negative 1. Okay, and this is my m tan. Now that I've got that, I can use my same formula to find my equation of my tangent line. Okay, so I've got y minus f of a is equal to m tan times x minus a. Okay, and I'm looking for when a is 1. So I've got y minus f of 1 is equal to m tan x minus 1. And I can plug in my values. So I know that f of 1 is 5. M tan is negative 1 as we found earlier, and that's x minus 1. Okay. So I end up with y minus 5 is equal to negative x plus 1. And y is equal to negative x plus 6. Okay. And so what we did was we found the equation of the line tangent to our function f of x at x equals 1. Okay. So there's a different method to finding our m tan. If we would have used the original method we had for finding m tan, would have given us the exact same answer. Would have been fine. Okay. Now, so we've defined our instantaneous rate of change 2 different ways, right? We defined it using the a and we defined it using the h. Well, now what we can look at is the derivative. Yay, we made it. All right, so we'll define derivative here briefly, and then in 3.2 later this week, we'll define derivative a little bit more rigorously. Okay, so we've got the derivative of f at a, denoted by f prime of a. Okay, so that little apostrophe, not a 1, little apostrophe, that's a prime. That's one of the notations for derivative. We'll talk about some of the other notations later this week. Okay, and so this derivative is given by either of the following two limits, as long as the limits exist and a is in our domain. So as for the limits exist and a is in the domain of our function, then either one of these will give us our derivative. Doesn't matter which one, they'll both do it. Look at that. Now, what are these limits? Well, think about this. So these limits are both our instantaneous rate of change okay, or the slope of the tangent line. And what does that tell us? Hey, look at that. So our derivative of f at a is going to be the same thing as our instantaneous rate of change, or the slope of our tangent line. Okay, they're all three the same thing. Okay. Now, we say that our derivative of f at a exists, or if it exists, okay, then we can say that f is differentiable at a. If the derivative doesn't exist, so one of these limits doesn't exist, or a is not in the domain, we then would just say f is not differentiable at a. Okay, it could be differentiable somewhere else, but not at a. Now, let's do some examples. We'll do 2 examples. Okay, and then there's more examples in the extra examples packet. All right, so we'll do 2 examples. This first one, we'll look and we'll start out. We're looking for the equation of the line tangent to the graph of f of x at 2, 2. Okay, so we know that our a is going to be equal to 2 and our f of a is going to be equal to 2 as well. Look at there. All right, so we're first got to find our m tan, so that's slope of the tangent line. Nothing's changed. Okay, so we can find the limit as h approaches 0. Either method will work here, but we'll do this one. Of our functions. Now in our case, we know that our a is equal to 2. All right, so we can plug our function in, and we get the limit as h approaches 0 of, we get 8 over 2 plus h squared minus 8 over 2 squared divided by h. Okay, and this is equal to the limit as h approaches 0 of 8 minus 2 times 2 plus h squared. That's 2 plus h, whole thing squared, divided by h times 2 plus h squared. Now, what we did here is the same thing we did a couple examples ago. We found a common denominator here and combined them and multiplied the whole thing by 1 over h. All right? Now, we do that and we get it combined down to 1 fraction. Woohoo! Now, you may be wanting, you see a 2 plus h squared here and a 2 plus h squared here. You may want to cancel. Do not cancel these. And why is that? Well, because this 8 over here doesn't have a 2 plus h squared, we can't cancel it. If it did, we could factor it out, but it doesn't, so no. Okay. Instead, what we shall do is expand it out and hope something cancels. So we get the limit as h approaches 0. If we expand it out, we get an 8 minus 2 times 4 plus 4h plus h squared divided by h times 2 plus h squared. Okay, and then we get a limit as h approaches 0 of 8 minus 4h minus h squared divided by h. We get our eights cancel, sorry. Now we can factor out an h and they will cancel. And so we're left with negative 4 minus h divided by 2 plus h squared, which I can then evaluate. So I can plug my 0 in, and I get negative 4 minus 0 divided by 2 plus 0 squared, which is equal to negative 4 over 2 squared, so negative 1. And that is our m tan, our tangent, the slope of that tangent line. Okay, so I can then use that, and we can find our equation. So we'll use the same equation, same formula for our equation we've been using, and we end up with a y minus f of 2 is equal to m tan x minus 2. So y minus 2 times negative 1, x minus 2, and that simplifies to y equals negative x plus 4. Okay. So this negative 1 down here, the slope of our tangent line, and guess what? It is also our derivative of f at 2, or at x equals 2. Okay. Now, don't worry. We'll talk about some easier ways to find the derivative in a little bit in this class. But for now, just know that that's what it is. Okay. So, our last example, we will again find the equation of our line tangent to the graph of f of x, or of f of x, same thing. So we are given this equation for our tangent line. Okay. And it wants us to instead find f of 2 and find f prime of 2. So we want to find our function evaluated at 2, and we want to find our derivative of the function evaluated at 2. So we will first start off with our f. So remember, so two things to note. Okay, so note. The tangent line and f of x meet at a f of a. Okay, so you know the tangent line and the function are going to intersect at that point. All right, at this point. So what this tells us, okay, what this implies is that f of 2, which is equal to 4 times 2 minus 1 is equal to 7. Okay. So we know that f of 2 is equal to 7, 1, because they told us, but also because if I've got some function, and line tangent at this point, let's say that's 2, 7. Okay, that point is going to be on both my function and my tangent line. Okay, so if I were to plug in 2 into my equation for my tangent line, it's going to give me back out a 7. All right, so that's the first thing to note. Okay, and we found that f of 2 is equal to 7. Our second thing to note the slope of the tangent line at x equals a, ran out of room, is the slope of f of x at x equals a. Okay. All right, so think about this in this way. We're looking for our derivative. What do we know about that derivative? So far, at least. For now, we know that it is the instantaneous rate of change or the slope of the tangent line. Well, what did this equation give us, or this problem give us? Well, they gave us our tangent line equation. So that means that my slope, which in this case is 4, okay, remember y equals mx plus b, where m is your slope. All right, so what does that mean? That means my derivative f prime of 2, my derivative of f at 2 is equal to 4. Okay, the slope of that tangent line. Alrighty, so that'll be it for today, for 3.1. In 3.2, we will talk more about the derivative and a couple other ways to notate it and define it. Remember, this week you'll have this video. Go ahead and you should have been filling in the notes as you went through. Make sure you look at the extra practice problems. These solutions will go up Wednesday, well, midnight between Wednesday and Thursday. Okay, and remember your learning activity is open and is due Wednesday at midnight. Okay, and make sure you join me on the discussion board Monday and Wednesday on this video, so discussion board in 3.1 with any questions you might have. All right, I will see you in either Zoom or on the discussion board. Have a good day.